Sarah Wilson, and welcome to the lesson on vectors. A vector is a quantity that has both magnitude and direction, and we represent them with an arrow. When we're talking about vectors for statics problems, we're talking about representing forces. The magnitude of the vector is represented by the size, or the strength of the force. And then the direction is relative to the coordinate plane. And so if it's maybe been a while since you've done coordinate plane, let's review that for just a moment. We've got on the coordinate plane an x-axis, which runs horizontally, and positive is to the right, and negative is to the left. And then on the y-axis, we have positive up above and negative down below. So, for instance, I have two example vectors here, two pretty basic ones. I've got one that's labeled 6 pounds of force in the horizontal direction, and it's pointing to the right. So if I were going to do any calculations with this vector, I would use positive 6 in an equation because positive on the x-axis is pointing to the right. Down here I have 3 pounds of force in the vertical direction pointing downwards. And so if I were going to do any calculations with this vector, I would use negative 3 in the equation. Now, not every vector is going to be perfectly horizontal or perfectly vertical. So what do you do if you have a diagonal vector? The key to working with a diagonal vector is that you want to break it up into its horizontal and vertical components. And to help people imagine what I'm talking about with horizontal and vertical components, I like to think about what if there was a soccer ball sitting right here. And I came up and I kicked that soccer ball with 10 pounds of force at this angle. Well, the soccer ball would fly horizontally, but it would also go up in the air. And so there's both a horizontal and vertical force in effect there. So we're going to try to find out, okay, well, if I kick it with 10 pounds of force at this angle, how many pounds of force is actually making it go up, and how many pounds of force is making it go sideways? So to do that, we're going to use some trigonometry. And the best way to help you visualize this is to take the vector that we've got here and to make it the diagonal of a rectangle. So this doesn't have to be perfect, it's just to help you visualize. So it's okay if you don't have to bust out your ruler or anything like that. But there's a rectangle. And you can see now, once we've drawn that rectangle, that you can see where the trig is coming in. We've got a right triangle right here. The things that we're trying to find out with the horizontal and vertical component vectors are two of these sides of this rectangle. This side right here represents the horizontal component, and this side right here represents the vertical. Now, to give them some names, we often call the vector that we're working with like F or something like that for force. And again, not everybody uses the same variables. Depends on who you're learning it from. But again, they're variables, so it doesn't really matter what letter you use. They're just standing for the unknown quantity. So I'm going to use F. I use just like a capital F to stand for the force that we're working with right now. And that would make this guy right here F sub x. That's a little subscript which stands for the force in the x direction. And this one I'm going to call F sub y, Fy, for the force in the y direction. So I'm trying to find out Fx and Fy. Alright, let's go ahead and concentrating on this right triangle right here, let's label those sides just like we did in the trig lesson. So I've got the right angle here. Straight across from that is the hypotenuse. I've got the angle that I'm working with, which is 20 degrees. Straight across from that is the opposite side. And then the remaining side, the one we haven't labeled yet, that's right next to the angle, is the adjacent. So let's go ahead and try to find Fx. That means I want to find the adjacent side. So compared to the information I know already, I have a hypotenuse, I'm looking for the adjacent. Which trig ratio uses hypotenuse and adjacent? Well, think about SOHCAHTOA. We're talking about the CA, which is cosine. So let's write the equation with cosine. I'll try to fit it over here for us. The cosine of theta equals adjacent over hypotenuse. And let's fill in the information we know. The cosine of 20 degrees equals adjacent, which is the side we don't know, that's our variable, so I'm going to just write Fx. And hypotenuse is 10 pounds of force. Now, just like in the trig lesson, we need to solve, get the variable by itself, get rid of 10 pounds of force by multiplying both sides by 10. These two should cancel each other away. And then in the calculator, all you need to do is 10 times the cosine of 20 degrees. My calculator's over here. 10 times the cosine of 20 degrees comes out to 9.4. So we're talking about Fx, the force in the x direction, comes out to be 9.4 pounds of force. And that's the whole point of leaving our units in there so you know what to label your answer. 9.4 pounds of force. I'll put that up here so that we have that information in the diagram. Now let's go ahead and find the force in the y direction. Now you might be saying, well, hey, wait a second, the force in the y direction is not actually part of this triangle. But remember that we made it a rectangle, right? Or at least it's supposed to be a rectangle, even if it's not perfect. And in a rectangle, the side right here would be equal to the side over here. Which means we can just go ahead and find the length of the opposite side, and it will be the same as Fy. So, opposite. And let's use hypotenuse again. Now, even though we do already have adjacent, we found adjacent just a second ago, there is a chance that we made a mistake in finding this value. So it's better to use the number that was given in the problem anytime you can. So let's use opposite and hypotenuse. So OH, which one would that be? That is so. So we're talking about sine. Sine of theta equals opposite and hypotenuse. There's that OH. And let's fill in the information we know. I've got the sine of 20 degrees equals opposite. And even though it's labeled over here, remember that this is really representing Fy, so that's the variable I've got there. Over hypotenuse, which is again that 10 pounds of force. Okay, it looks pretty familiar to last time. The only difference is that this is Fy now instead of Fx, and we're using sine instead of cosine. But same step to get Fy by itself, multiply by 10 pounds of force. Gotta sneak it in here, we're running out of space. So 10 pounds of force times the sine of 20. Calculator's this, 3.4. So I come up with Fy equals 3.4, and again, there's that pounds of force. So Fy we found is 3.4 pounds of force. So what this tells us is that if there was a soccer ball sitting here, and you kicked it with 10 pounds of force at an angle of 20 degrees off the horizontal, then 9.4 pounds of force would be propelling that soccer ball sideways in the horizontal direction, and 3.4 pounds of force would be propelling it upwards. The calculations that we just did with the right triangles, finding the component vectors, lead you to a couple formulas that you can use anytime you're looking for horizontal and vertical component vectors. For any vector f with the direction of theta, so f would be representing the magnitude, you can find the x component vector by taking the force times the cosine of theta, or the force, or like I said, the magnitude. And if you're looking for the y component vector, then f of y equals the magnitude of the force times the sine of theta. So cosine for x, sine for y. And there's a nice trick that if you measure all your angles from the positive x-axis in a counterclockwise direction, it's actually a nice way to stay consistent, especially if you haven't used any trig before this. Let's look at a couple examples up here. I have two diagonal vectors that we're going to find the x and y components of. The first one I have is 30 pounds of force at an angle of 50 degrees. But watch out, that 50 degrees is off of the negative x-axis. It's over here on the left side of the coordinate plane. So to be able to use my little note down here, the little shortcut that I have, I want to measure this vector, the angle from all the way over here on the positive x-axis. So let's go ahead and mark that. I'm looking for this angle right here. Alright, so to go all the way up here, that would be 90 degrees. And then I have a little bit more left to go. There's 50 degrees less than 180. So 180 minus 50 would give you 30. So 130 degrees is what this red angle right here is. 130. And that's the angle measure I'm going to use in the calculation. So I've got the force in the x direction, or the x direction component vector, equals the magnitude of the force times the cosine of theta. So in the x direction, I've got 30 pounds of force times the cosine of 130. Make sure to use that one. Okay, grab your calculator. And we've got 30 times the cosine of 130, which gives you negative 19.3 pounds of force. Now, why would it be negative? Take a look at the vector here. We're talking about the x direction, and notice how it's pointing off towards the left. So because it's pointing towards the left, if you remember that coordinate plane we had up there a little bit ago, left is negative in the x direction. So that's why we end up getting negative 19.3. Well, let's go ahead and do the y component vector as well. The force, or the component vector in the y direction, is the magnitude of the force times the sine of theta. And let's substitute in 30 again, just like last time. 30 pounds of force times the sine, and again, use 130, measuring from the positive x-axis. So 130 degrees. We end up with, calculator again, 30 times the sine of 130 is 22.98. So if I'm rounding to the nearest tenth, like I did last time, we're talking 23 then. So 23.0. The force in the y direction is 23.0 pounds of force. Now notice this one comes out positive. Why? Well, we're talking about the y direction here. And so this vector is pointed upwards. And as a result, you get a positive value for your y component vector. So force in the x direction, force in the y direction. And those two right there, those two vectors together make up that 30 pounds of force at the angle of 130 degrees. Let's do the same kind of thing for this vector over here. It's 65 degrees below the x-axis, below the negative x-axis over here, and it's got 52 pounds of force on it. So just like last time, I want to go ahead and measure all the way from the positive x-axis to the vector. And again, this is in the counterclockwise direction. So here we got 90, 180, and then an additional 65 degrees, and that ends up with 245 degrees from the positive x-axis. And that's the value I'm going to use for theta in the calculations. So let's do the force in the x direction equals the magnitude of the force times the cosine. Magnitude of the force this time is 52 times the cosine of 245. Alright, so calculator time again. 52 times the cosine of 245 comes out to be negative 21.976. So again, if you're rounding to the nearest tenth, we're talking negative 22 here. Negative 22.0 pounds of force. And again, there's that negative. And you can tell this one should be negative again because in the x direction, it's pointing slightly to the left, which is why it comes out to be a negative. In the x direction, the left is negative. And let's finish up with the force in the y direction. That's the amount of force, or the magnitude of the force, times the sine of the angle. So in the y direction, I've got 52 pounds again. That's the magnitude of the force. Times the sine of 245. So 52 times the sine of 245. And this time I get a negative 47.128, so round to the nearest tenth, negative 47.1 pounds of force. Now notice this time both Fx and Fy came out negative, and that's because both x is in the negative direction, pointing slightly to the left, and the y value is in the negative direction. The vector is pointing downwards. So you get negatives for both of them. Now one other thing I'd like to point out is that the calculations that we're doing here are almost exactly the same for both the x direction and the y direction. It's just the difference is for the x direction you're using cosine, and for the y direction you're using sine. I hope you've enjoyed this section on vectors. Next up, you can find a lesson on adding vectors.